This is a short discussion on what is simple harmonic motion. Now, our world is filled with a lot of different oscillations that repeat itself from going back and forth. So this type of motion is called a periodic motion. And that's a motion, as you see at the top of the notes, where the object repeats the same motion over and over in this cycle. Now there are a lot of examples that would show that, so let me just show a few graphs where you see objects oscillating about their equilibrium position. So you can see here's one pattern right over here, or another one over here, kind of this jagged pattern. And lastly, this case where you see it forming a nice smoothly varying sine curve. This is called a sinusoidal motion. And we're really going to be concerning ourselves with this type of motion because this has a special name. It's called simple harmonic motion. It's often abbreviated SHM, and this type of motion occurs when the restoring force is directly proportional to the displacement from the equilibrium. And also, the acceleration is directly proportional to the displacement from equilibrium. That means if you were to plot a graph of the acceleration versus the displacement from equilibrium, you would see that there would be this direct relationship between them. All these points would follow in a nice straight line. So, what are some examples of things that exhibit this periodic or oscillatory motion? There are a lot of things that vibrate in nature, and so you should be able to think of any kind of example where you have vibrations. For example, you could have a guitar string that vibrates. You could have also maybe just the wind blowing and across some power lines, and those power lines are vibrating, oscillating, and exhibiting a simple harmonic motion. We're going to be looking at two specific examples in this chapter. We're going to be looking at the simple pendulum, which you could think of when you look at your grandfather clock. That would be a simple pendulum. And also we'll be looking at a mass attached to a spring. So really there are two examples. We have the mass attached to a string, which is a simple pendulum, and then mass attached to a spring. And here's another picture, by the way, of someone oscillating a car, because there's shocks in the car. So there's the mass of the car, and then the springs are the shocks, and as you push up and down on the car, you can make it exhibit simple harmonic motion. And by the way, just a quick note, if I refer to something as a simple harmonic oscillator or just an oscillator is just basically an object that undergoes this oscillatory or periodic motion. Okay, let's now move on to some of the important properties that we will see in simple harmonic motion shown on page 2. So some important terms that you'll need to know. First off, the amplitude. The amplitude is the maximum distance that the object will move from the equilibrium position. It's typically measured in units of meters. So if you think of that car bouncing up and down, it would be the maximum distance above or below the equilibrium position when the car is at rest. The period, abbreviated with a capital T, is the total time to complete one full cycle or one full oscillation, and it's measured in units of seconds. Frequency is the number of cycles per cycle, per second, and that is measured in hertz, which is the same thing as one cycle per second. And you'll notice that frequency and period very closely related. The frequency is inversely related to the period. So F equals 1 over T, and that is one of the equations on your AP formula sheet. There is another term that we'll be seeing in this chapter as well that is quite useful, but it's not part of the AP Physics B curriculum, but I think it would be important to know, and that is known as the angular frequency. That is the number of radians that would be completed if you were to observe the motion in a circle per second. So that's written as rads per second, and we use a little small w. This is actually technically an omega, a small version of that, but you could just look at it as a w. And it is equivalent to 2 pi times the frequency, which is also equal to 2 pi divided by t. Now this formula is not on the AP formula sheet, but you'll see as we go through this chapter it might be a very handy one to know. So go on to examples 2 and 3 and see if you can calculate what the period, frequency, and angular frequency for each of these, for examples 2 and 3. So I'll go ahead and write down the given here. We have t equals 1.40 seconds, and we're trying to find in part A, I guess we'll say this is a part A, what is the period, which is actually given. That's 1.4 seconds. And then B is asking for the frequency, which is 1 over the period. So that's 1 divided by 1.4 seconds, which gives you 0.714 hertz. And the last part is the angular frequency. That's 2 pi times the frequency, or you could do 2 pi divided by t. It's up to you. So 2 pi divided by 1.4, which gives you 4.49 rads per second. Okay, go on to example number 3 now. Hopefully you could do this on your own. Maybe stop the video here and see if you can actually do this on your own. Read the question and interpret what they're giving you and find the different things that they're asking you. Okay, so you're told that it's 200 times per second that the fly is flapping its wings. You have to interpret that as some piece of given information. It's a number of times, which is really like cycles per second. And something that cycles per second, remember we defined earlier as the frequency. So the frequency is given actually. 200 times per second, we can really call that actually 200 hertz. Okay, so we already know the frequency. So now we're moving on to the period. The period is 1 over the frequency, so 1 over 200. And remember that hertz is the same thing as 1 over seconds. So 1 over 200 is going to give you 0.005 seconds. Okay, and the last piece of information we have is the angular frequency. The angular frequency is 2 pi times the frequency. So that's 2 pi times 200, which gives you 400 pi. You could leave that as 400 pi rads per second, or you can convert that into decimal form, which comes out to about 628 rads per second. Okay, one more part. Now let's visualize the kinematics of this motion as a graph form. So you'll see two types of graphs in simple harmonic motion. You have the snapshot graph, which is a snapshot of what it would look like from the vertical, if like a very aerial view. If you were to look at the y on the plotted on the y-axis and the x on the x-axis, and if you were say to take a picture of the say vibratory motion, this graph is actually not showing that. This is what I like to call a history graph. It is showing what is happening to the position of the particle as it moves back and forth from the equilibrium over time here. So this is time, and notice this is written in milliseconds, so this is times 10 to the power of -3 seconds. Okay, we're asked in this question to find different things. We're asked to find the amplitude. Remember that the amplitude, abbreviated with a capital A, is the maximum distance from equilibrium. So along here, this is the equilibrium. So how far does it reach away from it? So it could be positive 0.4 or as low as negative 0.4. So that amplitude is just the maximum distance, which is 0.4 millimeters. Okay, part B is asking for the time to make one complete cycle. So the period is, if you were to start here and look at this when it starts to reach the same position again and start to repeat the pattern, oh, there's one entire cosine curve. And so then again, another entire cosine curve, and then another entire cosine curve. So you can see going from here to here, or from here to here, or from here to here, you can see that it undergoes 2 milliseconds. So this is really 2 to the power of -3 seconds. Okay, now sometimes if you have a lot of these, you might want to count, go 1, 2, 3 cycles, and then divide by 3 if it's hard to read this instead of just doing 1, because that'll be more accurate. Okay, part C is asking for the frequency. The frequency is 1 over the period. So since you already know the period, you can substitute that into there as 1 divided by 2 to the power of -3 seconds. That'll give you a frequency of 500 hertz. And lastly, we have D, the angular frequency. The angular frequency would be 2 pi times the regular frequency. So that's 2 pi times 500 hertz, all right, which you could write as 1,000 pi rads per second, or you can convert that into decimal form, and that comes out to about 3,140. We'll round that off to just 3 sig figs rads per second. And that's it for examples 2, 3, and 4 in our brief introduction of simple harmonic motion and some of the kinematics of that.